Thank you everyone for coming today. We really appreciate it. We are presenting CalcBox, an open source talking calculator for the visually impaired. So we'll start off by who we are.
So I'm Gillespie. I'm a senior here at Grandview. I'm interested in cybersecurity and computer science. I started programming when I don't even remember how old I was. I'm a Salesforce certified administrator, and I'm also certified in NVDA and JAWS, which are two screen readers for Windows. After high school, I plan on attending the Arapahoe Community College for cybersecurity and continuing work on projects such as CalcBox.
I'm Yoder. I'm also a senior here at Grandview. I'm interested in computer science and cybersecurity. I've participated in several extracurricular activities like Cyber Patron and volunteered for Steel City Codes. I have my CompTIA Security Plus certification, and I'm going to Purdue to study computer science. So a little bit about why this is needed. The current solution for the Orion TI-84 talking calculator has a couple of problems, one of which is that it's very expensive and rare. It's about $700 if you're even able to find one. They're not really produced anymore, so they're hard to get your hands on.
They're also pretty clunky. It's based on an old version of the TI-84, which means it's pretty thick and it's powered off batteries. In addition to it being powered off batteries, you also have to charge it just so it will talk to you. All the buttons feel the same, so it's very hard to memorize the layout. I just have to count the buttons, which takes a good amount of time. And the text-to-speech is unstable because they're using software from the 90s for it, so it tends to just crash.
Yeah, and so our original goal is to build a replacement for a TI-84. And so where can we improve on the Orion calculator? Well, to start, we can improve on cost. By building this from scratch and designing it to be a low manufacturer made-to-order product, we can save immensely there. We can also save money by ditching unnecessary components like a screen, because that's not as necessary as it is for everybody else.
We can also improve the ease of use by making the buttons feel distinct, which we actually have succeeded in doing. Initially, we wanted to put Braille, but that didn't quite happen. We want to specifically design the interface for speech instead of basing it off the TI-84's interface, which was designed to be shown on a screen. And we also want to make it hackable and open source because we both obviously are more technical people and love it when we can just hack our own devices.
So now we'll move on to project objectives.
So on the software side, I wanted to learn to write C++ code for microcontrollers. I learned C++ on Windows a bit, but I didn't know too much about microcontrollers at all at the start of this project. I wanted to get an awesome project on my resume. I wanted to improve math for blind people as someone who's gone through math as a blind person myself. I wanted to majorly improve my teamwork abilities because up until now, all my work has just been on my own, most likely sitting at my desk in my room. And I wanted to change that a little bit. And I also wanted to learn how to write code to output through speakers, which, because it's something I rely on speakers a lot, and I wanted to figure out how they work from a technical perspective.
And as for me, I also wanted to learn how to work on a team and integrate several parts of a project together. I wanted to learn how to communicate both through a written journal style and also a presentation style. I wanted to learn how to use CAD software, because that's a part of technology I've never touched before. I've always been focused on the code side. And I also want to learn how to make functional circuits with microcontrollers, and then how to also code the very low levels of those circuits. As for advisors, we have Martin Fink in the back. He has been incredibly helpful. He is the former CTO of HPE in Western Digital, and he's also the board on Platform.io. He's also on the board of directors for Platform.io. He has about as much experience programming in C as the both of us do living combined, and so he's been very helpful.
Yep, for our other expert advisor, we have Stephen Clower, who's a blind software developer at Desmos. He works on making the website accessible, Braille mode, and Desmos' web-based graphing calculator, so he's been incredibly helpful on this project.
And then we have each other for support, and then we also have Ryan for kind of an outside opinion as someone who's taken this class before, and then Lewis, who's been incredibly helpful with the 3D printing and 3D modeling project. So as for our original timeline, by the first 5 weeks, I wanted to create an initial prototype so that Ty could write some code for it. It wouldn't be complete, but it would be something that he could work with. By week 9, I wanted to design the circuit and the PCB. By 13, I wanted to have the basics of the case all ready. And then I wanted to spend another 3 weeks just on the buttons. And then at the end, I was hoping to assemble everything together, make it actually work, and then also work on this presentation.
So for me, my original 5 weeks were basically just setting up everything I needed, learning everything I needed, because I'd never done anything with microcontrollers before, so I had to learn a lot in the first 5 weeks, set up a development environment. I'll go a bit more into some of the problems I hit with that in a bit. In weeks 6 through 9, I wanted to actually start making a calculator, have the basic math functions, have it support clearing, etc. In weeks 10 through 13, I wanted to add scientific functions and maybe explore graphing. I left weeks 14 through 16 kind of open-ended, in that it was a little bit of extra time in case I needed to do something, but if I didn't, I wanted to explore adding effects to the audio to make it sound cleaner. And then in week 17 through 20, I decided to just clean up anything that needed it and prepare for presentations.
All right, so now we're going to talk about what I've been doing this last year on the hardware side. So, to start off, we can look at the original plan for the architecture. So we wanted to use an ESP for all of the processing. An ESP is a microcontroller. It's much like an Arduino if you're familiar with those, except it's a bit more powerful and has some extra features. We were going to have that take in the button input, then process the text-to-speech, and then output it using the built-in DAC. This DAC, all it does is takes the digital signal and makes it an analog one so that we can put it through our speakers. And so yeah, the ESP has one built in, so we thought it's probably pretty good and we should use that. And so in order to talk about how buttons work on the Copbox, we need to talk about how you would normally program buttons with an Arduino. So typically, you would take a button, hook one side of it up to power, and the other side of it up to a GPIO pin, and when we press the button, the GPIO pin could detect that the circuit was completed and electricity was flowing through it. And so that works really well when you're dealing with very small numbers of buttons. A TI-84 has about 60 buttons, and so if we were to try to use that, we would just not be able to because we don't have any microcontrollers that have 60 GPIO pins. So we had to use a different solution, and that solution is a button matrix. What you do is you hook up buttons in a 2D grid with one side of each button up to a column and then one side up to each row. Then you put a bit of power onto your columns. With that, you can check each of the rows in order to see if there is a voltage detected. If there's not, you move on to the next column and then repeat this process. And then you keep going until you detect either a power or you just move on. If you detect that voltage line, you know which power line was lit up, and then which row was also detected that, so you know the 2D coordinate of that button. And then you can process it from there. And so with this, we are actually able to make our initial prototype. This right here is what Ty was working on for the first couple of weeks, or what he programmed on the first couple of weeks. I assembled it in my basement for 3 hours one day. And it has a 3x5 button matrix, which is not even enough for a 4-function calculator, but it's enough for testing, and that's what it is used for. And like I said earlier, it uses the built-in DAC. As it turns out, that sounds awful. It has a lot of static, and so it's actually really hard to use because it's really annoying and loud. So we had to change our plan. We used the I2S interface in order to hook up a DAC. Like a DAC is just another processor. And so we can just take that off ESP. And so I2S is a very common interface for having DACs communicate. All it does is just makes the chips talk to each other. And yeah, it's fully digital and works really well. And then we had to pick a DAC. Luckily, there was a list on one of the libraries we were using that had all of the DACs that were supported. There was only one of them that met our needs, and that was made by Adafruit, and unfortunately they discontinued it many years ago. Luckily, if you throw its name into Amazon, there are a lot of knockoffs, and those work really well. And so that's what we're using. We're using a knockoff Adafruit DAC. From here, I was able to work on the schematic and PCB design. All the schematic is it's a diagram of circuits and how they connect to each other. And then a PCB is when you take like a physical board and they etch a circuit into it. So instead of having a bunch of wires everywhere, it's held within the board and you can put components onto that. And so I used KiCad in order to design both of these things. And I was able to do it in a couple weeks. And ultimately, I was able to send my board off to be ordered, shipped, and then I assembled it myself. Down here is, so that's the board. And I plugged it in, assembled it, uploaded code to it, and then absolutely nothing worked. Everything just wouldn't give me any signs of life. I thought I destroyed the microcontroller. And I would be in this spot for several weeks. And ultimately, over those 3 weeks, I found a lot of issues. And I'm not going to go into too much detail about them because it's more than is needed, really. But most of them have to do with using pins that were reserved for other purposes. If you want to hear about those, you can totally talk to me about my table about that. Anyway, the point is, I could have probably eventually made it work. But by the time that I gave up, I was 3 weeks in and I hadn't even discovered all the problems. And so it would have taken me forever. And even if I was able to make it work, it would have just compromised quality. It wouldn't have been any good. And so it's pretty much a full failure. And so how did this happen? A technical catastrophe of this level is no longer a technical issue, but a procedural one, because I didn't catch it. And so I prepared a very helpful graphic in order to discover what went wrong. The first thing was a lack of research. I kind of went through this project as if I kind of could learn as I go, but that turned out to not be the case. Then I didn't test everything. I did test each small part of it, but I never did everything in a big test altogether. Then the third bit was rushing. About 2 months in, I had a physical electronic board, and that was exciting. And then so I just kind of kept going forward really fast, and that ended up being not great. And ultimately, this led up to an unearned confidence that ultimately underpinned most of the problems with this. So we had to start over. It wasn't an easy decision, but it just had to be done. And so we came back with a few guiding principles. The first one, go slowing. Passion is a fire that burns bright, but it burns very hot and very fast. And so in order to limit myself trying to rush through and just get excited about it, I actually only worked on this in class and during the weekends for at least a little bit while I got back up on my feet. Next is to go small. Now we just have less time, and so it needs to be more simple with less complexity. So that means less buttons, and when I ultimately ended up designing the buttons, I wasn't going to put Braille on them anymore, because that just would take too much time. The next is test everything, and I think this is the biggest one. If I threw everything together to be tested, then I would have caught most of the issues beforehand. And so everything I did needed to be tested before I would order anything. And then the last thing is to have other people look over it. There was a ton of people in and out of this class who wanted to help me on this project and who knew a lot. And they could really help me see things that have been too tunnel vision to see before. And so now, I have a new timeline. Ultimately, the biggest thing from this is I just had to take what I did before and squish it into some less time. So, yeah. So now I have a new architecture. Instead of having the ESP do everything, we split it up. The ESP still handles text-to-speech and audio processing. However, we now use the Teensy 4.1 in order to process the math and also the inputs. And Teensies are actually used by people who build their own keyboards, so it's actually great at handling button matrices. And so from there, we were able to design this new system. In order to have these chips communicate, we used the serial interface, which is an old interface, but it's very simple and very reliable. And so from that, we were able to have the chips communicate, and so it tells it what to say, and yeah. We also used batteries, of course. So we wanted to use AA batteries instead of rechargeable batteries because I don't know if everyone knows this, but batteries like to catch on fire if you overcharge them or put too much power to them. And I really wanted to avoid that at this point because we didn't have enough time, and also I don't like fire. And so AA batteries is very simple power delivery, and so we ended up using that. An issue with any type of battery is that as you use it, the voltage decreases, which is a problem when all your components expect 5 volts. And so we ended up using this little Adafruit mini boost in order to step up that voltage so that it always gets up 5 volts as expecting, even if the batteries are outputting as low as 2 volts. And from here, I threw everything onto a breadboard. And so I got to test everything, and if that means putting it onto 5 breadboards, that's worth it. And so yeah, now here's a couple of optimizations I was able to make after I had a meeting with Kurt Brisnicker. He is the chief architect at HP Labs. One of the things he suggested to me was the addition of bypass capacitors. Basically, if a power spike were to happen on your chip, the batteries are generally not able to keep up. Like they can't keep up with that spike. And so if you add a capacitor, that capacitor will charge up and it can discharge much faster than everything else. And so if the circuit were to spike, it would draw power from that capacitor first. and then it would, well, the battery catches up and then it would draw from that. And so you can actually see the capacitors there, or the yellow things. And the other thing is with my trace resistance. If you were to try to hook up a garden hose to a fire truck, it would just explode, right? You just have too much water running through that. The same thing is true with electricity, except instead of how thick your garden hose is, it's how thick your traces are, how thick your wires are. And so originally I had very thin wires there, and that's a problem when you're pumping a bunch of power through them. And so I ended up making them much thicker to accommodate that more. And another thing that I had no idea about was if you have a through-hole component, which just means that there's no, they drill a hole through the board so you can stick your component in. When you have that, there's no conductor in the middle. And so you need to add copper around the edges there in order for the electricity to flow through that. And ultimately, that led me to be able to make this board, and this ended up working really well. I'm very happy with it, and now that all that was left is the case. At this point, I didn't have much time, so it's a lot simpler. I use Fusion 360 because it runs on my computer, and also because it's free, so there's a lot of tutorials, and also people in the class know how to use it. This was a very simple design. It's a box with some clips that snap together. That's it. And so when you put them together, they'll just snap together and pull tight. It works really well. An issue is if you don't print it, when I 3D printed it, I didn't print it with enough plastic in the middle, and so it ended up snapping at first, but that was an easy fix. I just print it with a higher infill, more plastic in the middle, and it works great. And then I designed buttons. At first, I drew them on paper, and then I digitized them so I could put them into Fusion. And so I could design the shape of the profile of the buttons without using the tools in Fusion itself. When I needed to make the buttons concave so you can feel how they're different, that's when I ran into some problems. It's actually really difficult to make concave items in Fusion. You have to define a point off of a plane, and that's just a lot of work for 48 buttons. I just didn't have enough time. So I ended up settling on a bit of a hack where I extrude a cut at an angle and then use the fillet tool to kind of smooth it out. And this ultimately created it gave me wildly different results depending on the exact angle I used, but ultimately it works pretty well. And so at the end, it cost about $85 for the materials to build this. And I consider that a pretty great success. Just having this for $85 is amazing. So ultimately, we started back at the original prototype. Then we moved on to the first version, and then nothing worked. So we have to go back to the drawing board, test everything, move on to the board again, design your case, and ultimately, now we're back here, and I'm pretty happy with how it turned out. So I'll throw it on to Ty for the rest of the time now.
All right, so for me, on the software side, my timeline didn't end up changing too much. The first 5 weeks were just the preparing, learning everything I need to know, etc. Because, well, mainly because we hadn't started hitting issues by this point. In weeks 6 through 9, I implemented the basics of a calculator with basic math functions, clearing, etc. And then I kind of learned my lesson a bit later in the project that it's good to just have a bunch of time set aside. So I set aside weeks 10 through week 17 to just work on it and work on the software and fix any problems that came up. And then in weeks 18 through 20, I prepared my final presentation. So now, for choosing a development environment, I initially started out using the Platform.io CLI, which was basically, I would just type commands and it would do things to my microcontroller. However, if you ask any of my friends, I have one of the weirdest computer setups ever, and so it didn't work all that well, mainly due to missing drivers. After a couple of days of fighting with it, I just got annoyed and ended up switching to the Platform.io VS Code extension. It's the same tool, it just has a different user interface on it, one that I don't tend to like as much, but it does completely work. I can upload to basically any microcontroller, I can write code, and I can test it, and it works great. Now, for the onboard text-to-speech, we started out using the eSpeakNG library, but this would prove to be a problem, because in the beginning, we were running everything off the ESP, the single ESP32, like Grant said. And so it was just too intense for that little microcontroller to be able to run the speech and be able to calculate at the same time. So we ended up moving over to a speech engine called Flight, or Festival Lite. It's not as good of a speech synthesizer. It's smaller, but it doesn't sound nearly as good. It doesn't have as many settings, but it did work for the prototype, and so we were pretty happy with that. Now for the external text-to-speech, like Grant said, we switched over to an ESP32 just due to limited power. And it communicates just over serial. Serial's a really old protocol. Like Grant said, it's older than I2S. And because of that, it's just super reliable. It can support both flight and eSpeak. The current calculator sitting over on the desk does support eSpeak because in the past couple weeks we've ported it. But when we initially started with the H2 hardware, it used flight. And it imitates something called the double talk protocol. The double talk was a synthesizer for that was in a lot of embedded blindness devices back in the 90s. It was basically what this speech chip that we have is, except with a different synthesizer that I and many others really like the sound of. We managed to find an open specification of how the protocol worked online, and so in the code, I'm specifically following that. We also have plans to turn it into a standalone product, so you could just go and you could buy a chip, plug it into your device over serial, and get speech. Now for expression evaluation, this is one area where having a bunch of extra time also proved quite handy because on the initial version, on the ESP32 that we were originally using, I could use this C++ library called TinyExpert, which stands for Tiny Expression Evaluator. And an expression evaluator basically just takes a string, like 1 plus 4, and returns the result from it. It does whatever it does. That I unfortunately had to learn to do that. And I was using this library, and it worked great. It had a lot of functionality, and I was really excited about it. I became a lot less excited about it when we switched microcontrollers, and it literally just would not work. And no one could tell me why. I looked on Stack Overflow, and I only ever found one post even mentioning this issue, and the solution they proposed caused the board to crash, so it didn't quite work. I ended up just writing my own expression evaluator after spending a couple weeks fighting with it. As such, it's not nearly as good as it could be. I found a couple things that don't work, but it generally supports PEMDOS, and it works well enough for a basic calculator. You can even register custom functions, which we do for power currently, but we don't do for anything else. I thought we did for square root, but it's seemingly kind of broken. But it's working pretty well. Converting, so one problem that I hit as well is that text-to-speech processors weren't specifically, or text-to-speech engines rather, weren't specifically written for a calculator. They were written, they just read exactly what you feed to them, which is why also I'll just hear nothing when people have fancy nicknames on my Discord, because a text-to-speech synthesizer just says, here's text, I speak text, and that's about all it does. So I had to write a little speech processor. When it takes a string, before it gets spoken, it gets fed into this processor. And what the processor does is it will see, oh, okay, is what's spoken here part of, for example, is it the multiplication sign, which is in our calculator represented with like a little asterisk. And if so, we convert it to, say, times. Now, this worked pretty well. It took me, it's a decent bit of code, so it took me a little bit to write, but it works pretty well. The only problem I hit with it was that I had to learn kind of the hard way that creating the map of characters and doing the processing without any caching was pretty expensive on a microcontroller. Honestly, it probably would have been fine on virtually any Windows computer or any just desktop or laptop, but since we're running on such a limited computer, I kind of figured out, oh, I need to make this a bit more efficient, so I optimized the code a bit. And it all now completely works. I can talk a bit more about the specific optimizations at my table, but it works really well, and it was a really good thing that I'm glad to have learned, because now it will make me write more efficient code just across the board. For supporting multiple boards, since, as I'm sure you noticed, we went through a lot of different boards and microcontrollers and configurations, and even between the initial prototype board and the new one, we were using analog versus I2S or I2S audio. So we had to figure out a way to switch between them. And this isn't so necessary now, now that we're just using the one board and that's kind of our main focus. But for a while, there was just this little header file. You could say, okay, I'm building for this board, or I'm building for that board. And it would know, all right, here's how I communicate through audio, and here's the pin we use. Platform I/O also really helped with this, because we didn't need to make separate scripts or whatever to build for this board or to build for that board. Platform I/O just handled a lot of it. and it was pretty great. I've been very happy with that for my own. Now for handling input, like Grant talked about the button matrix, but I didn't really have to worry about that. What I had to worry about is the actually how you make it so the calculator speaks what you press and types keys. So for that, we're using the Arduino keypad library, which has a function in it called isPressed, and you just give it a key, and it will say, yes, this key's pressed, or no, it's not. However, I didn't know about this initially, and so I tried to write a function that was just, it would do basically the same thing. And it worked, with one caveat. The caveat was that it would constantly say that the key was held down after that. It would always return true after that key was pressed once. And I never was quite able to figure out what the keypad library does to avoid this. And I want to at some point, but since I was on such a time crunch, I was just super glad it worked. Now, for writing menus and the history class, I wrote a super customizable menu class, and I tested it initially on Windows. It's just, it can show menus through text-to-speech that you can navigate and select items in. And it mostly works on the calculator. It's not used in too many places yet, but it can support vertical or horizontal navigation, so you can navigate it through with the left and right buttons, the up and down buttons, or all of them. It can optionally wrap around if you wanted to do that. And there are plans for customizable sound support. I want to, for example, have sound packs so you can select different sound, like if you want your calculator to sound different. However, this just hasn't been done yet. And I also wrote a complete equation history class, and what that does is it can store basically an unlimited number of equations. There's a limit, but it's in the billions. So if you're worrying about that, then I don't quite know. And you can insert either the given equation or the result of said equation, and it won't even have to recalculate it. It'll be really fast because it's all cached. And yeah, it works really well. There are still a couple little bugs with it, but it works really well overall. One thing I want to do is make it so that it repeats what item you're hitting at the edge, because currently if there's only one item and you press up or down, it sounds like the history is empty, which is not ideal, but it works pretty well. Now for linker troubles. The linker, this is something I can talk more about at my table, but the linker is basically what takes all your code and turns it into something that can be ran. And the linker for the TNC doesn't support what are called exceptions, which are essentially just a way of saying, oh, here's an error. I just throw an exception to indicate an error. And it turns out the TNC linker doesn't support them. After about 5 hours of digging through blog articles on, I believe, a Thursday night, just randomly, just trying to figure this out after weeks. And I eventually found out that the TNC linker just doesn't support exceptions. There's a technical reason behind it at the processor level that I won't bore you with because I had to learn it and I don't want you to have to. But so I just ended up temporarily removing them, which is why currently when it gets an error, it will just say 0. But I will, I'm going to, especially over the summer, I plan to look on forums and just see if I can manage to figure it out. Another problem I had is that I had this at the very beginning, but just kind of ignored it. When I tried to have multiple files, like I have a history file and I have one that has the main firmware, it would just throw a bunch of errors, like 45,000 characters of errors, and I could not figure out why until randomly, I wasn't even looking for this, but I was just browsing on the TNC forums, and I found a post that said that .ino files are compiled at the same time as each other, and .cpp files are compiled separately. Well, that's really good information for me to know, and I figured that out, and I changed all the file extensions to .ino, which essentially stands for Arduino, and now it all works.
So now we have a little demo, and I would...
6 times 8, 48. 9, 9, divide 1, 1, 9. 5, 5, minus 0.1, 2, 54.88. Speed control.
So yeah, you can change the speed on it as well.
And you can change the volume.
7 times 6 times 4, 3,120.
So, yeah, that's really what we ended up having.
Yep.
And
now for a final evaluation. Oh, sorry.
No, you go ahead.
So for me, at the very end of the project, I feel pretty good about this project. There's a lot more I want to do with it, and I'll get more into that in a minute. But on the software side, I ended up learning a lot more about embedded programming, which is awesome. That's something I wanted to learn for a while. I learned how to use Platform I/O, which is a tool I didn't even know existed at the beginning of this project, and I'm super glad to have learned it. I learned much improved time management, except for the times when I get driven crazy by trying to debug something, but in general, I've made improvements there. I learned much more C++, which will help me in a lot of my future projects. And I learned how to push past all the setbacks, do everything not working, and continue anyways.
As for me, I learned how to design a circuit and get a PCB fabricated. I also learned how to use Fusion 360. Again, it's not something I've touched before. I learned how the iterative process of designing software or hardware is different from software. I learned how to organize information in a presentation, and I think the biggest thing I learned was how to bounce back from a big failure. So ultimately, for future plans, we'd like to build out the rest of the calculator, have more math functions, and also try to make the case design a bit better.
And we also want to design proper audio circuitry instead of just having a DAC and that outputs to headphones only. We want to have an onboard speaker. And we also want to use an amplifier as well as a DAC, so it'll sound better. And like I said earlier, I want to improve how it sounds, how the raw output sounds. We'll really see how it sounds after putting an amplifier, and that will kind of determine. Want to reduce the noise floor, that'll come with that as well. And we do want to turn CalFox into a company, probably a pretty small one, like maybe just a nonprofit, LLC or whatever, but there's a lot of room for innovation in accessible technology, and I think we can do a lot with it.
Thank you. Are there any questions? Yes, Joe?
So do you guys have plans on expanding this so it's not just a scientific calculator, but it can use like cosine, sine, trig?
Yes, we do hope to, yeah, go ahead.
Yeah, we really want to expand it. The initial goal for this project was actually to make something that would replace the TI-84. And I do have to give Mr. Combs credit here. He told us that probably wasn't going to work, and we did not listen. And but yeah, we do eventually want to expand it to that. I have a lot of ideas about how to implement graphing as a blind person, as someone who's used existing solutions. For example, I want to use 3D audio, which means you hear it in three-dimensional space. But that's something I want to explore further down the line. Yeah.
Yes, over there.
So are you, how much do you think you could make in return, how much do you plan to make in returns if you plan to make a company out of this? Like if you want to do the improvements and how expensive would it be? Because I know you said it was $85 for the whole frame. So how expensive are you looking for improvements and all that stuff? How expensive?
So luckily, a lot of the improvements we want to do actually don't require any extra hardware. They either just require a redesign or something similar. And so the price or the bill of materials wouldn't actually increase all that much, if at all. And so it would mostly be on the software side.
Yeah, it would be definitely, the whole goal is to be cheaper than existing solutions. I'm honestly not 100% certain how far this will go. For example, for graphing is pretty intensive, so we might need another microcontroller, so that could bump it up. But even with all of that, in the worst case, I think we're probably looking at, definitely looking at something that's way cheaper than the existing solutions. $729 last I looked. And I would honestly be pretty happy with selling them for about $200 if like 150 or so of that was being purely just hardware costs even.
Yes, okay.
So what exactly is the highest form of math you can do right now?
So in theory, sine should be sine should be working, except we're having some issues with it on the actual board. Right now, it's basically a 4-function calculator, but it can also do exponents.
And it supports, I actually could use it for algebra homework, I suppose, because it does support PEMDAS at least.
Mm.
I have one more question.
Yeah, absolutely.
Can it do decimals?
Yes, it can.
Even with and without trailing zeros, that took me, I had to manually code for that. It's given me a lot of appreciation for things that just work now.
The only thing I think doesn't work with decimals is decimal exponents. That seems to be giving us incorrect answers.
Yeah, you can also, the only other bug I currently know of with it is if you have a number outside of parentheses, it doesn't get multiplied properly. But I'll probably fix that. I'll be able to fix that. I already kind of know how. So
Over here.
So you mentioned not being able to use Braille a certain number of times.
Mhm.
How does the method you decided to use work as a work?
it works pretty well, honestly, because if you go and you see it at the table, actually, there are lines. So some of the buttons just feel completely solid. Some of them have like the middle cut out, so you can feel it's just hollow in the middle. Some have just lines on the top or lines on the sides, and some also just have different designs on them. So it's not Braille, so it's not nearly as good, but honestly it works really well. I've actually, as I've had it and been messing with it, I've been able to navigate more and more quickly just as time goes on.
Over here.
This is Miss Jeannie. I have a question. Both of you wanted to work on a team to see what it was like, and what are some learnings that you found working on a team?
I'll start. I think the biggest thing I learned is how my decisions really impact everybody else. Like when I made mistakes and I messed up and had to start over, that really hit Ty in his workflow.
Yeah, but I would agree with that. That's one of the big things. Or for example, when I was completely stuck on software, I couldn't, like I kind of had to learn how to just ignore the fact that my code doesn't work and it's driving me absolutely insane, and be like, okay, no, we wanted to set up the buttons this way or this would work. So it was kind of one of those things I really learned how to manage priorities and also just how everything works together.
Over here.
You said that if you had more time, like redesign the buttons.
Mm-hmm.
Would you redesign the buttons in Braille?
So yeah, at least something like that. Also the mounting solution I probably want to redesign. There's a couple of things that are, by the time I started on the case, I think I had 3 weeks left, so they were kind of rushed.
Let's go one more question.
One more.
All right, good deal.